So welcome back, all of you. It's a pleasure to welcome Professor Poonam Chandra from the National Center for Radio Astrophysics. And her areas of interest have been on transients, and last winter school she gave a talk on radio transients. So she's been working on supernovae, the circumstellar interactions, acceleration mechanisms. She has worked extensively on gamma ray burst and electromagnetic counterparts of gravitational wave sources, and more recently on radio magnetospheres of massive stars, where she has arrived at a lot of interesting results along with her student Bernali Das. And so it's a pleasure to welcome you, Poonam, to speak to us about radio emission from stars today. Thank you very much.
Thank you, Sykes, and good morning, everyone. So we will be talking, as I said, about, as Sykes said, radio emission from stars, and I have added a little bit and beyond because I will be talking about a little more which are relevant for these stars. So first of all, I would like to show you this image, and this is not an optical sky. This is the radio sky, Curti scenario. And unlike optical sky, which is dominated by starlights, the radio sky is dominated by radio galaxies, which are far, far away, ionized hydrogen clouds, supernovae remnants, and so on. The reason that we don't see stars in radio sky is because stars are extremely weak emitters in the radio band. That's because, for example, if you look at the stars, there are examples of 3 stars with surface temperature 5000 K, 6000 K, 7000 K, and you can see that they're all near optical band, and the radio emission, if you see the wavelength at the radio, the black body emission is going to be very, 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 very weak. So it means the stars will, in a traditional way, the way they emit black body radiation, the radio luminosity is going to be very, very weak. It is very important to understand these radio stars because they allow us to explore a parameter space which is unavailable by any other means. So let's just try to understand a little bit of the stars, introduction to stars. This diagram on your right, if you see, is one of the most famous, one of the most popular and important diagram in stellar evolution. This is called Hertzsprung-Russell diagram. And this strip which goes from top left to bottom right, this is called a main sequence strip. And the stars here are the main sequence stars, which are burning hydrogen into helium. So hydrogen to helium fusion is going on in these stars. And these stars have masses from around less than half solar masses to over 100 solar masses. And the low mass stars lie on the bottom right, and the high mass stars lie on the top left. But one thing you notice here is that in the x-axis, the temperature is not going the traditional way left to right, but rather the opposite, right to left. It means the temperature is increasing as you're going more left and left, progressively on the left side. So this is just for, I believe, historical reasons. So one of the things here to note in this HR diagram is that the stars which are much more massive, which are on the top left, they have a smaller lifetime, whereas the stars which are on the bottom right have a much longer lifetime. In fact, the stars which are less than half solar masses, they are still in the main sequence phase because the stars have such long life that they are longer than, their lifetime is longer than the current age of the universe. So these stars have not had a time to complete their evolution. Sun lies somewhere in this, I don't know if you can see my cursor or not, but the sun is a 1 solar mass star, lies somewhere in the middle. The interesting part in this diagram is the stars which are heavier stars, because they will have a very different kind of end of their lives as compared to all other stars. And I will come to that in a bit. But I would also like to say that the stars are classified as, you don't have to remember it, but just for the sake of completeness, this O, B, A, F, G, K, M, and the O stars are the hottest stars, most luminous stars, shortest lifetime star, whereas as you go progressively, colder and colder stars, they have the longer lifetime, lower luminosity, and so on. So let's try to see what is going on. So for example, in our sun, we know that the energy we receive is because hydrogen fusion is happening and it is burning into helium. And on the right hand side, I am just showing you example of how hydrogen burns into helium in sun. It is called a PP cycle. And so this is, again, I think at this level, you probably don't have to really worry that much about the PP cycle and so on, but I'm just showing you this diagram. But one more thing, what is happening in sun is that it is losing its outermost layers, and with the rate of 10 to the power minus 14 solar masses per year. And that you can see, one can observe in the form of solar winds. The sun has already lived its half its life, around 5 billion years, and it has another 5 billion years to live. And at that time, hydrogen will exhaust at the core, and the sun will there will be no more hydrogen fusion at the in the helium. Finally, there may be a little bit of helium burning, but eventually the sun will become majorly what is called helium white dwarf, and that will be the end stage of sun. If you take stars which are more massive than sun but less than 8 solar masses, hydrogen burning is taking place here also, but this cycle is generally called CNO cycle, where C, carbon, nitrogen, and oxygen work as catalyst. They also make white dwarf at the end. However, here there is more advanced nuclear burning is taking place, which means not only hydrogen is burning into helium, but helium also burns into carbon and oxygen. So the white dwarf will be called carbon oxygen white dwarf. And it is very interesting because these white dwarfs, if they come in the vicinity of a companion, then these white dwarfs will accrete mass from the companion, and then they will explode. There's something called Chandrasekhar mass limit, and because of that effect, they will explode as what is called thermonuclear supernova. And these supernovae have very important place in cosmology. They are called standard candles, and they have told us a lot of information about our universe. But the most interesting, the icing on the cake is taken by the massive stars, which are 8 solar masses and above stars. These stars at their core have such high densities and temperatures that not only hydrogen burns into helium, but the nuclear fusion advances to much higher stages, and it stops until silicon burning into iron. But the fusion takes place at a very fast pace, so they have a very short lifetime, as you can see in this table and in this plot. And these stars undergo a very complex death after doing all of these fusion. And what happens is, in a very simple terms, again, these are very simple ways. I have not taken into account the rotation, magnetic field, binarity, and many other aspects. But in a very simple terms, if a star is less massive, say less than 30 times mass of the sun, it will going to explode as a supernova, and it'll leave a neutron star at its core. If it's more than 30 solar masses, it is going to leave a gamma ray burst. It is going to explode as a gamma ray burst, and it will leave black hole at the core. So this is the death of massive stars, which is a very explosive death. The difference between supernova and gamma ray burst is that supernova is a non-relativistic explosion of the star, where in a very simple terms, what is happening is that when the nuclear fusion has stopped after silicon burning into iron, the whole of the star is coming together and density is increasing. And once it reaches the nuclear matter density, there is the center part core acts as a wall, and the rest of the matter hits this wall and explodes. And it explodes with supersonic speeds, at the speeds of the order of say 20,000, 30,000 kilometers per second. But still, they are non-relativistic speeds. And in this case, the explosion is very more or less symmetrical in every direction. Whereas at the core, if the star is much more massive, this explosion is relativistic explosion, and it is beamed. And also, when the explosion is relativistic, it's moving with around 99% of the speed of light. At that time, there is something called relativistic beaming which takes into place. So you see this very collimated kind of explosion, gamma ray bursts. And so we will be able to observe the ones only which are pointing towards Earth, and we will be missing all the gamma ray bursts which are pointing away from Earth. But these are the two stages of massive star explosion. Another thing which happens is that all the elements which were being produced at the core of the star in these explosions, they become available to the environment. And so when the next stage or next generation of star formation will happen, star will be formed, the star will be the stellar system will be having much more heavier element. For example, sun has lot of heavy elements, so it means it must have been formed in a space where there must have been some supernova explosion which has already polluted the environment with heavier elements. And these heavier elements can only be formed inside a supernova explosion, inside a massive star. And during these explosions, they are made available to the medium, to the surrounding. So this is the origin of heavier elements in our universe. These stars, as I said, will also make neutron stars and black holes, and some of them rotating neutron stars. One study in the form of pulsars in radio emission, and I am sure you will be having some talk about pulsar, where you will learn more about this. So let's come to the type of radio emission. One I have already told you is the black body emission from the surface of the star. And but in this case, the emission will be very, very faint as compared to the early in the radio band as compared to the other bands. But the radio emission does not have to just come from the surface of the star. The immediate vicinity of the star also plays an important role. For example, as I said, the stars are losing mass because their outermost layers are not that gravitation, not tightly bound due to the gravitation. So even sun is losing its mass, which is 10 to the power minus 14 solar masses per year. But intermediate mass stars and massive stars, they lose mass with much more higher rate. They can reach up to the order of 10 to the power minus 5 solar masses per year or so. So by the time a star has evolved, from its from main sequence, it has already lost its considerable amount of mass. And this mass which is surrounding a star plays very important role. They can reveal themselves in the form of radio emission and emission in the other wave bands. And in addition, these stellar winds, the mass loss from the star can also carry magnetic field, and they will also reveal themselves in some other some ways, including the radio emission. So because of these, what kind of emission can take place? So again, because of this mass loss of the stars are surrounded by the plasma, and radiation from this plasma, if it has in a very traditional way, if it has Maxwell's particle distribution, it is called thermal radiation. If it has a non-Maxwellian particle distribution, it is non-thermal radiation. And from in a very simple term, if for example a Lorentz force on a charged particle is given by this electric field as well as the magnetic field, and if this charged particle is accelerated, it will produce radiation. And I have shown you the radiation for the non-relativistic as well as the relativistic case. And the two main things happen here. If the acceleration of the charged particle is mainly due to the Coulomb field, then one will have what is called Brimstone radiation or free radiation. And if the acceleration is due to the magnetic field, one will have gyromagnetic radiation. Now, Brimstone, I think you may have already been familiar with this, but I'm just going to give a very broad overview. So, for example, in this plasma, there are electrons and there are ions, and these electrons, when they come in the vicinity of these ions, these interactions of electrons and ions that will deviate the path of the electron, and that will give rise to the radiation. And that radiation is called Brimstone radiation. Of course, this radiation, if there are direct encounters, they will produce much higher energy radiation, but radio emission will be little more gentle and distant kind of collisions. And I'm showing you here the emission coefficient for the Brimstone radiation, but the thing to note here is that it depends very strongly on the density of the star. So it is a very nice probe of the density of the star as the star is undergoing its stellar evolutionary stage. So if one can observe many stars and one can see Brimstone radiation, you can have a lot of samples and densities of the stellar, of the surrounding at different stellar stages of stellar evolution, and try to understand how the stars are evolving, how they're losing mass, and so on. Now, gyromagnetic radiation is that in the Lorentz force factor, if the magnetic field part dominates, if the acceleration is experienced due to the magnetic field, then these electrons will gyrate in this spiral motion, and then they will have the radiation, which is called gyromagnetic radiation. And in this case, like in some cases, these radiations may overcome or may be much more dominant than the Coulomb interactions, and then the gyromagnetic radiation will take place. It does depend very strongly on the particle energy, whether the electrons are non-relativistic, mildly relativistic, and ultra-relativistic. The ones which are important for us, for stars, are gyrosyncrotron emission and synchrotron emission. Gyrosyncrotron emission will happen if the electrons or particles have achieved mildly relativistic speeds, and this is what actually one sees in most of the cases, radio emission from star. Then there is another kind which is a little more extreme, which is called synchrotron emission, where if the electrons have reached relativistic energies, then the radiation will be synchrotron radiation. And for example, in gyrosynchrotron radiation, electrons have to reach energies of no, I think I have written wrong. It's not KeV, it's MeV, because electron rest mass itself is 511 kilo electron volt. But in synchrotron radiation, it has to reach of the order of GeV kind of energies. And synchrotron emission can happen in these stars, but under very special conditions. It is the gyrosynchrotron which is more prevailing. Another thing I would like to say that so far what we saw, Brimstone or gyromagnetic, here each electron is acting separately and producing the emission. And then when we have to estimate the total emission, we have to add the contribution from each electron. But it is also possible for electrons to act together and produce electromagnetic radiation in some kind of electrons being in phase and then emitting radiation in one go. And this is called a coherent emission. In this case, if you, how do we know that an emission is coherent emission? If you estimate brightness temperature. And what is brightness temperature? Brightness temperature is that imaginary temperature of a system or of an astronomical system, which if it was emitting black body, how much its temperature would have been. So it means you can imagine that if a system is majorly emitting black body, the brightness temperature is going to be same as the actual temperature. But in other cases, brightness temperature is quite high. And as long as when the brightness temperature exceeds what is called 10 to the power 12 Kelvin, then these radiations are coherent radiations, and they could be electron cyclotron maser emission due to the magnetic field, and they could also be plasma emission due to the high density of the plasma surrounding. So now what I'm showing you here is HR diagram for radio stars. And again, this is it is the same thing. The left, the temperature is high on the x-axis, the right temperature is low, and the y-axis is showing some kind of luminosity or magnitude. The circle size and whether circles are filled or unfilled are indicating the radio emission and or quantifying the radio emission. The open circles reveal the thermal emission, radio thermal emission, that is, like you can imagine, mainly Brimstone, free emission, and filled circles are non-thermal emission, and the bigger circles are more emission, and smaller circles are less radio emission. So this is how this HR diagram of the radio emission is, and you can see that these brighter, more massive stars generally tend to, in the main sequence at least, they tend to dominate the radio emission from the stars. So in this now, I'm going to say the two things. One is that the nuclear fusion is happening at the core of the star, and how these photons or energy is reaching at the surface, that could either mainly by radiation or by convection. And in less than half solar masses star, most of these photons are they reach the surface through convection. But in, for example, our sun kind of star, the inner zone is radiative zone, but the outer zone is convective zone. These two situations are different than heavier stars, where inner zones are convective, but the outer zones are radiative. One of the thing is that in the convection, there are these dynamo effects are taking place. So these stars do acquire magnetic field. They become magnetic stars. Like sun has magnetic field, and most of the low mass stars have magnetic field. But these bigger stars, which have radiative outermost layers, they should not have magnetic fields, and most of them actually don't have magnetic field. And in this talk, I'm not going to talk about the low mass stars, because one, you are going to have a talk on sun tomorrow by Ramesh, and in that talk you will be covering most of the radio emission from the stars. And if you cover the sun, most of these low mass stars with convective outermost layer will have the same processes. So I'm not going to come to that. I'm just going to cover the stars which are heavier, which have radiative outermost layers, and they are also in the classification of the stars. They are O, B, and A kind of stars, or mostly O and B stars are the ones I will be covering. They are very important in our understanding of our universe, because one, even though they are very few in numbers as compared to the average star, but they dominate the luminosity. They have very fast forward, very fast evolution, and they show extreme in many aspects. They have violent deaths, they have very strong stellar winds, and they are the ones which explode. They have advanced nuclear burning going on. So they have, when they explode, the medium becomes chemically enriched much more by these stars. So they have a very decisive role in the reionization of the universe. And they are also, since they're so bright, they can be seen from a faraway distance. Radio emissions from massive stars, they have very strong winds. Most of the time, these winds are, because mass loss rate is high, these winds are optically thin, and the radio emission will be thermal, generally free emission, which will have some part of it will be absorbed as per the Brimstone radiation. And this is what one will detect the radio emission from these stars. And they do give, as I told you just a few minutes ago, their density of the medium. That means they tells us about the mass loss rate of the medium. However, when we are talking about the massive stars, we have to talk about some other factors in addition to mass loss rate. Those are rotation, metallicity, binarity, and magnetic fields. And in this talk, I will be mainly covering magnetic field and binarity, because they do affect radio emission directly. Other things have more indirect kind of effect on the radio emission. So let's start with the magnetic field. But the problem is that how can we start with the magnetic field when I have already told you that these stars have outermost radiative layers, so they are not expected to have magnetic field. But the nature generally throws us with some surprises, and it has been seen that so there are several surveys of these massive stars. These are a spectropolarimetric survey from different kind of telescope. One of them is Canadian French Hawaii telescope, the spectropolarimetry in those telescope. And these surveys have shown of these massive stars in our galaxy that around 10% of such massive stars have magnetic field. And these magnetic fields are very simple dipolar magnetic field, but they are high magnetism. They are kilogauss kind of magnetic field. So they are simple, stable, unlike sun, which has a lot of magnetic activity going on. These are very simple dipolar magnetic field. And other thing is that this dipolar field, the magnetic axis are tilted with respect to the rotation axis, and this is called in literature called what is called oblique rotator model. And so there are some consequences of this magnetic field, but one of them is that why are we interested in understanding the magnetism of massive star? One, since this is a talk about the radio emission, and radio emission is one of the best tracer of the magnetic field in our universe. So this magnetism is certainly very important to study when we are talking of the radio emission. But and there are other reasons also. For example, we know that there are magnetic white dwarf. We know that there are magnetars which have very high magnetic field, and their origins are still debated. And these magnetic stars, these 10% of the magnetic massive stars, could provide those channels to understand this evolution of such stars, which will probably end up as magnetic white dwarf or magnetic magnetars. Second is that these stars will have a very little different kind of evolution, because it is possible that because of the magnetic field, they will lose some of their angular momentum, and these stars are generally known to be slow rotators. Magnetic field, there is another very important aspect of the magnetic field is that the plasma is going to follow the magnetic field lines. So if it is a dipolar magnetic field, the plasma will flow through these dipolar magnetic field lines. It means these massive stars, which were losing their mass profusely, mass loss rate, is going to be reduced because this plasma is trapped in this magnetosphere of the star and not able to leave the star. And this has very important consequence, because if you're keeping up to date with the literature, you know that gravitational waves have been detected from several, roughly around 50 black hole mergers. And all these black holes, which I'm showing in the bottom right diagram, the blue circles, these, it has been found that the LIGO, the black hole, the LIGO is the instrument which has detected gravitational wave. These black holes have much higher mass, and we do not understand the formation of these 2030s kind of solar mass black holes. So if these magnetic massive stars are quenching the mass so much, they could also provide one of the channels of making heavier mass black holes. So it is very important to understand this magnetism, and what does this how does this magnetic field is arising. We don't know, but one of the theory is that the cloud, the dark nebula from which the stars were formed, these dark nebula were slightly more magnetic than other nebulae, and this is the due to the conservation of magnetic field, these stars got magnetic field. There is also recently, this theory has picked up much more, which is called stellar merger theory, where when the two stars are merging, they can their differential rotation can create some orderly magnetic field, and it has been shown in simulation by Schneider et al. That this is possible to generate dipolar magnetic field in merger, but it is still not clear which of the channels or whether both channels are there to create magnetic field. But what does the magnetic field do? One, I have already said that the wind, the stellar wind or the star, the mass which is lost from the star, this plasma will follow the magnetic field lines. Now there will be, so this will create a magnetosphere around the star, and which is what we are most interested in, because that is most important for the radio emission. There will be a part of magnetosphere where the magnetic field will dominate, which is called inner magnetosphere. There will be a part of a region where the wind will dominate, and that is called the outer magnetosphere, and this boundary is called Alfvén surface. If you don't remember it, it's okay, because I will be repeating this again, and I will be probably talking in more physical terms, which you don't have to remember, the alpha surface and so on. But what is happening because of this magnetic field? What is happening is that because there is this magnetic field and these electrons are following these magnetic field lines, as you can see in the left figure, these electrons are colliding, and they are producing the X-rays. They are also creating this region where these electrons can get accelerated, and it turns out that electrons can get accelerated to mildly relativistic energies, and these electrons can produce this gyrosynchrotron kind of emission. And since the rotation axis is misaligned with the magnetic axis, and our line of sight, because of our line of sight, we are seeing this misalignment, the radio emission is going to be modulated. For example, which I have shown in this figure, because of this misalignment, this radio emission is generally modulated from in these stars, and because of their radio spectrum, and we also see some circular polarization in this gyrosynchrotron, which is of the order of 25%. We sorry for the spelling mistake in the temperature here. We do see this variability in the radio emission. So this gyrosynchrotron is a manifestation of magnetic field in massive stars, and this gyrosynchrotron generally takes over the any kind of thermal emission the star is having, the thermal Brimstone emission I was just talking some time back. But there is another more interesting kind of manifestation of magnetic field, and that is coherent emission, which just now a few minutes back I told you about, and this is electron cyclotron major emission. So in this, the idea is that the electron, when they're coming back on the star, the electrons in a very small region, they will be reflected back and they will be lost from the system, and there will be something called lost cone anisotropy. The overall effect is that they will be in this middle figure, you can see in this circle, which is called this cone ring, and from this there will be this coherent emission, and this will be highly directed coherent emission, nearly 100% circularly polarized. And the way the geometry is such that they will fall on the magnetic null. So in the right hand side, I'm just showing you a cartoon diagram that how we will see these kind of electron cyclotron major emission. And this was considered to be very exotic emission for the reason that the first massive magnetic massive star, a B star, showed electron cyclotron major emission in the year 2000. After that, there were searches, but for 15 years, there were no such star, no second such star which showed electron cyclotron major emission. But then in the year 2015, we speculated that there is probably, we have seen another star. If you see the right side diagram, this is the one where we speculated that this is probably showing ECME. And then my student Bernali did more observations, and she confirmed that this is indeed a second star which is showing electron cyclotron major emission. And this is extremely interesting result because one, it is the electron cyclotron major emission at different frequencies come from different stellar heights, and it is very sensitive to the magnetic field and the density, and so it does provide the conditions of the plasma. Second thing, as you can see, the base emission is much smaller than this electron cyclotron major emission. This means you can observe the stars which are far away. You can probably see many of the stars in radio emission from LMC, SMC, and maybe slightly other galaxy also, with if you have the enough sensitivity in the radio telescopes. So with this, more surveys have been done, and many more, and our Indian telescope GMRT has played a very important role in discovering these electron cyclotron major emission. And I am very happy to tell you that while in the year 2000, there was only one such star to show this kind of coherent emission. Now we know 15 such stars, and out of those 11 have been discovered with the GMRT. And these are now, we have named them as main sequence radio pulse emitters, or MRPs. So this is a very new kind of field where the magnetism of the star is being used to understand the properties of the plasma. As I said, electron, cyclotron, laser emission at different frequencies will come from different heights, and they will tell a lot about information. For example, here I'm showing you one star, which is, I'm showing you at different frequencies. The topmost frequency is the lowest GMRT frequency. The bottommost is the VLA frequency, which we have done the observation. As you can see, this electron cyclotron laser emission has a cutoff. And then with this cutoff, one can constrain the density of the plasma. So this is a very, very important probe to understand these stars, the main sequence stars, even though they're very weak emitters, but we can get so much of more information about these kind of stars. Now, there is another very important aspect. I hope I have some time. Yes, there is another very important aspect in magnetic massive stars, and that is binarity. And binarity is something we cannot ignore. That's because these stars are forming from a dark nebula. So many stars are forming together, hundreds to thousands of stars. So the chances that they are in a binary system are very, very high. In fact, it has been shown in multiple papers that more than 2/3 of these stars lie in a binary system. So these massive stars are, they prefer to be in the binary system. Now, if you have this magnetism and you have the binarity, one has to understand the interplay between binarity and magnetic field. Especially, it is quite important if you have a closed binary system. So again, there was a survey done with of the binary stars, and it has been found that there are around 12 to 15 such systems are known, in which one of the star is magnetic, and in these closed binary stars. And but we have seen that only 1.5% of the total binary stars, massive stars, have magnetism. So this is something one needs to understand. But the interesting thing is that if you have a closed binary system, the magnetosphere is going to give rise to the gyrosyncrotron emission, as we saw in the single star. But these stars, these winds are also going to interact, and these wind interactions will create shocks, and their synchrotron emission can take place. If the magnetospheres are interacting, they are so close that even their magnetospheres are interacting, because of magnetic reconnection, one can have incoherent and coherent emission. So there are so many things we need to disentangle to understand, and this is a very interesting problem in stellar evolution, and one needs to understand that. So this image is not a typical image of a binary system, because if you notice here, both the stars have magnetosphere, whereas in general you will have only one out of the systems we know, only one such a star has two magnetospheres. Rest of the time only one star has magnetosphere. So you will not have the magnetosphere interactions in that case. Yeah, I think somebody needs to mute. Anyway, so we know only one such star, which is very close binary system, orbital period 4 days, and both the stars are magnetic, and this is called epsilon Lupi. And radio observations of these stars have shown this kind of one. They have shown this cyclic variability, which could be connected with the rotation period, and they have also shown these two peak structures, which are coherent emission, which is most likely due to the magnetospheric kind of interaction. So this is a very, very new field which is coming, and it is telling us about how these magnetospheres are interacting, and this has the maximum potential to throw light on the origin of magnetic field of these stars. So now that I have talked about the binarity, I've talked about the magnetism, and this field is very, very, new in the radio astronomy, and that's why probably after many years in RWS we are talking about these stars, which is not sun-like stars, and we are massive stars in radio emission. And now I'd like to move to a little different understanding of these stars. And what I'm going to say that it's not just the evolution of these stars which give us information about these stars. Even this death of the stars can give us information about these stars, and radio emission plays very critical role because it gives us information about what we call E-cube, energetics, environment, and evolution of these stars. So these stars, if you remember, I told you they will have explosions. It could be supernovae, gamma ray bursts. They will leave neutron stars or black hole, and these neutron star black hole could also have a second deaths or second explosive deaths. It is important to understand them because they are the sites of extremes of physics. They involve high relativistic velocities, extremely energetic events. They have relativistic electrons, extremes of magnetic field. So they do give us information about the physics at its extreme. And I'm going to tell you how the radio observations have played a very important role. So one is that we know that supernovae are exploding from massive stars. But if you see in this diagram, the stars are losing mass quite profusely. And sometimes what happens, the star could lose all of its hydrogen envelope, sometimes hydrogen plus helium envelope. So we don't understand that when the star exploded, what stage it was in. The nature of the progenitor is unknown. You can get some information from spectroscopy, but still the how the star evolved to what how it is at the time of explosion is not known. Another thing is, since the star is losing mass, the main sequence star and the mass the star which exploded, there is no mapping, and mass loss rate is the most important but most uncertain parameter. So radio emission is most sensitive to the density which is created by the mass loss of the star. So it is a very sensitive probe of the mass loss rate of the star, which is carrying the footprints of the progenitor star. So what I'm trying to say is that the radio emission is probably one of the best way to understand the progenitor of different kind of stars are exploding in which kind of supernovae. And so if you study this post-death radio emission from these stars, that is supernovae, at different times, different scales, one can in some way recreate the history of the progenitor star, and not just recreate history in a very fast forwarded way. So let me just take a second and explain you what I'm trying to say here. So imagine a star is at the center and the star is losing its mass and the form of wind, it is moving. It is moving with a speed, say 10 kilometer per second, just to pick a number. Now the star explodes, the supernova ejecta, which is moving with say 10,000 kilometer per second. So the difference in the speed of the wind and the ejecta is 1000, which means if I observe this star one day after it exploded, I am going to get probe the wind or mass loss of the star 1000 days before the explosion. If I am going to study it 1 year after the explosion, I'm going to probe how the star looked or how the star was losing mass 1000 years before the explosion. So this way, by studying a supernova for a few years, I can understand these stars and their evolution before they exploded for a much longer time, and can try to understand their evolution. So this is one of the best ways to probe in radio emission. So this is just one. I'm just showing you a light curve and the spectra, and I have deliberately picked the one where a very simple model does not fit the data well. So I'm just trying to say that we have reached a stage where we have started to do, or people have started to do very complicated modeling to understand these progenitor star systems and how their densities are changing with time. So if you take a very simple evolution of the density, constant mass loss rate, this is the model with a constant mass loss rate. You see that the earlier and the late data do not fit. It means the mass star was not losing mass at a constant rate, and one needs to understand these kind of things. So this is how we are studying supernovae and trying to understand the progenitor. We are also trying to understand the gamma ray burst. Now the gamma ray burst, if you remember, I had told you that if a star is much more massive, it will have a relativistic explosion, a collimated explosion. And and create likely a black hole at the center. Now, the problem with these gamma ray bursts are that they last only for from a milliseconds to minutes or at most a few hours. And in the gamma rays, and that is the time they stay in the sky. And now, after a lot of understanding studying, we kind of think that we understand that there are two kinds of gamma ray bursts. Gamma ray bursts from massive stars coming, which I told you, and also if the neutron stars are merging together, they can also create a gamma ray burst. If you remember that there were second kind of supernova also, thermonuclear supernova, but I didn't talk about those supernovae because none of those supernovae have been seen in the radio band so far. So I didn't, but in the gamma ray bursts, I'm talking about both because both kind of gamma ray bursts have been seen in the radio bands. Now, the problem here is that gamma ray bursts last for such a small time that it is not possible to understand their properties in such a short time. So what we do is we go for the afterglow of these gamma ray bursts at shorter frequencies, and this is what we try to understand. And on the right hand side, what I'm showing you is a 3D a frequency, time, and flux or intensity diagram for a synchrotron. As you can see, synchrotron moves to lower and lower frequencies at later and later times. What does it tell me? It tells me that radio emission, which is a lower frequency emission, will still be bright at later and later time, and one can probe a gamma ray burst in radio emission for a long time. And that gives us a lot of information. Again, the radio observations are the most sensitive probe of the environment, that is how the star evolved, and they give us information. Radio emission in this case, in fact, all the emission in gamma ray bursts are synchrotron emission because electrons reach such high relativistic energies. So this is just an example of studying a gamma ray burst, and this is gamma ray burst studied from GMRT frequencies to ALMA frequencies, and you can see that GRBs are so fast evolving things that earlier we could only understand their density in one time stamp, like one epoch. But now we are able to, with sensitive telescopes and with a lot of studies, we are able to understand their density evolution, which means how the progenitor star must have evolved, how the environment of these progenitor stars must have been, with great detail. So this is the study. This is how GRBs are studied, gamma ray bursts are studied, which tells us about the very massive stars, which are very few in our universe, but very important, play one of the most important roles in the universe. And gamma ray bursts are so bright that they provide us one of the best ways to understand the stars at very early universe. For example, the gamma ray burst, which is spectroscopically confirmed GRB, the farthest gamma ray burst is at a redshift of 8.3. This happened in the year 2009, and that is the redshift which corresponds to age of universe only 0.63 billion years. And currently the universe is 14 billion years. So you can imagine that a star exploded at that epoch, and which we observed in 2009, and that also tells us that at that time in the universe the star formation was already taking place. So this gives us very important and very interesting information about these stars, these radio emission. I think in the last few minutes I would just like to just touch something very interesting, and that is that I told you that all supernovae will make a neutron star. In a very simple terms, gamma ray bursts may leave black holes. And what happens is that there is a possibility, because of their high gravity, that these black holes could merge together. These neutron stars can come together and merge, and they will create an explosion. Of course, black hole explosion we will not be able to see because there will not be any photons, but the neutron star explosion is going to produce electromagnetic radiation, and one can likely see this radiation. So on 17th August 2017, there was a event where two neutron stars merged together. It produced gravitational wave, and it also produced electromagnetic counterpart. So it produced photons and gravitational waves, and it remains the one and the only event. But it was only so this event was studied in all frequencies possible in the electromagnetic spectrum. But some very critical information come from the radio observation. One of them was that the very soon after this event was very behind the sun, so all these optical telescopes could not observe it, but the radio telescope could still observe this. Radio telescope could still observe this, uh, and with radio observations, it was very clear to us that initially what we are seeing when two neutron stars are merging, in that merger the jets are coming out and jets are losing their energy to the medium, and this medium is producing the radio emission. And late time observation showed us that these jets are successfully coming out. It means, it may not sound very interesting to you right now, but what I'm trying to say is that it was for the first time, it was a confirmed evidence that the merger of two neutron stars indeed do produce these jets, and short gamma ray burst takes place in these jets. So these radio observations did provide very critical information. They also constrained the density in the best way possible, which was not possible by any other means. So these events have provided us very important information about the stellar evolution of massive stars. And what I'm going to say is that we are still observing these events. Many telescopes are observing these events because we do expect late time radio emission from these events, which will provide us very, very important information about the very nature of these progenitor stars. And we have not yet seen it, but we are waiting to see it. And with that, I would like to just end my talk with this following summary, that even though I have shown you that the radio emission from stars is weak, it explores a parameter space which is not possible to explore by any other means. It is one of the best traces of the plasma magnetism and properties. And we have seen the coherent emission. There's no other way to explore the plasma and the main sequence of the star at such great details. The explosive death of these massive stars in radio band also gives us information about the energetics environment of the progenitor and how the progenitor was evolving. And I'm very happy to tell you that our Indian telescope GMRT, for which you have already heard a lot and you must be hearing probably more, has contributed very significantly in this field, in these areas, and made many new discoveries and explored a lot of unexplored parameter space. And now a square kilometer array is going to take this field forward with this much better sensitivity and resolution. And India has a large involvement, so it is going to benefit the Indian researchers a lot. And with this, I'll end my talk, and thank you very much, and I'm happy to take questions.
Shirma, could you please go back to the slide where you showed the gamma ray burst? So in this, what is the cause of the asymmetry between the non-relativistic and relativistic case?
So there are two things. One is that in gamma ray burst, what is happening is that there is an accretion disk around the black hole. And because of this accretion disk, the perpendicular to the accretion disk, this magnetic field will be entangled, and the radiation, the plasma will come out in these, in these very tight magnetic poles, you can say. And other thing, what is happening is, since this is coming out with so much of energy, that there is something called relativistic beaming, which means any radiation, even if it's a radiation, spherical radiation, will be beamed, and it will be inversely proportional to the Lorentz factor. It means higher the Lorentz factor, larger will be the beaming, or smaller will be the angle in which these particles will be moving. So because of these two factors, where the radiation which was generated itself was collimated due to the black hole, and also the relativistic beaming, you see a very highly collimated, within couple of degrees collimation of these gamma ray bursts.
Uh, and the reason why the accretion disk forms in the case of massive stars is the only factor determining factor the mass of the star, or are there like other factors which contribute to
No,
the
no,
accretion?
mass of the star is at that depends upon the dark nebula. That is accretion disk is forming around the black hole, because beyond the black hole shorter radius, all this angular momentum has to be conserved. So matter cannot just fall on the black hole directly. So it will be rotating around the black hole. The accretion disk, I am not talking of the protostars and all those things where star formation is critical. Means at that stage.
Around a black hole, and that causes this gamma ray emission.
Yes, but there are also some theories which I haven't talked about, where magnetar, which is a neutron star but 1,000 times more magnetic field, can also create a collimated kind of explosion, and which will be called a gamma ray burst. So there are also many such theories.
Okay. Just to clarify, it's not the supernova which is causing this collimated beam. So after the supernova, the black hole which forms, that accretes matter, and that accretion disk causes this gamma ray burst.
Supernova, yes, it is. In the simplest picture, it is the black hole which will have this accretion disk, and because of that, you will have this collimated emission. There will also be supernova associated in some gamma ray burst, and that has been seen. But the supernova is more or less symmetric, though it has been seen that actually no supernova explosion happens if it's a completely symmetric case. But asymmetries are much smaller in supernovae than gamma ray bursts.
Okay, thank you.
Sure.
Question. So you had said that in coherent emission, the brightness temperature is much more than the actual temperature of the source. So, like, is this what is done to determine whether the radiation is coherent or incoherent by comparing the brightness temperature to the actual temperature?
Yeah, that is one way. That is certainly one way. And brightness temperature is high because flux is so much higher. So as long and then this limit comes from inverse Compton catastrophe. But another thing is that if an emission is say 100% circularly polarized, and if it is a directed emission, which is what we expect, say for example, in this electron cyclotron maser emission. So these directivity and high degree of polarization are also the property of this coherent emission. Because in many cases, you will not have direct access to the brightness temperature. You may put a limit on the brightness temperature, and we are generally able to put lower limits on the brightness temperatures. But then the directivity and polarization are a very good tracer of these emissions too.
What is meant by directivity? Like, how would we know that it is directed or not? Because we are only looking at our line of sight.
Yeah, you're right. I'll just show you this plot. So I was showing you that here, for example, in this, if you see the rightmost one, this blue and the red, these are the ones. So how the electron cyclotron major emission is being produced is in this cones, which are along the magnetic pole in the center plot, and there it is coming, in some way parallel to the magnetic equator, you can see. So this blue and red lines this is the direction. That is what I'm calling directivity. And since rotation axis is not aligned with magnetic axis, you will only see when this radiation is towards your line of sight. So that will happen. It's like a pulsar only, right? In pulsar also you see this highly directive radiation, these pulses, if you want to call it. So what I mean by directivity is that you'll see these pulses of radiation, and from which we will know that this is coherent emission. I think I may have so this, if you see, there is this radio emission, but then there is this highly directed or pulsed kind of emission. Gyrosyncrotron will not have such very sharp change with the time or rotation period of the star.
Okay, so if it wasn't directed, we wouldn't see such sharp pulses. Like we would still see radiation, even if the magnetic axis is like away from it. Yeah. Okay.
Exactly. Yeah.
Okay. Thank you.
Sure.
Are you using the array aspects of GMRT, or is a single dish sufficient?
No, we are using full GMRT array for sometimes what we do when we try to do at 2 frequencies. For example, in this case, we do subarray mode of the GMRT, where we put say 15 antennas at one frequency and remaining 15 antennas at other frequency. What we have done is we have only done observations at GMRT band 4 or band 5, which is basically bands around 600 megahertz and 300 megahertz. And the reason is that these GMRT has circular feeds for these two frequencies, and we are interested in circular polarization. For higher frequencies, you go to VLA observations, and there also we use subarray mode. So that's only to not have any time dependent effects which can change any plasma condition, just to confirm, just to make sure of that. But otherwise we are using the full interferometric array.
I mean, in the sense that a single dish may not help. Is that another way of saying it, or not like that?
One is single dish. Yeah, single dish will not help us because there is these regions are lying in very regions of high radio luminosity, many other sources, and we also need a pretty high resolution to be able to distinguish these sources. So we are not going for single dish telescopes at all. Yeah.
Ma'am, I had another question regarding the gamma ray burst. So, in the gamma ray burst, do we see a continuous emission, or is it in pulses?
So gamma ray burst, the thing is that you will only see if a gamma ray burst is looking towards us. So in that, so it means you will see a continuous emission, but that emission will be very, it's not a smooth emission. It's going to be like there will be a lot of structure in that emission. So even if you see for a few seconds, but I'm talking only of the prompt emission. The afterglow emission, which is more like synchrotron, which is happening because these jets which are interacting with the medium and creating the shock from which the emission is happening, there will be much more smooth emission. I can probably show you here. So this is, for example, this is not a very highly structured emission. These are much more smooth emission because these are coming from the afterglows. But this, if you see, these are the prompt emission for few seconds. They have lot of structure, different kind of structure. Some GRBs have one peak, some have two peak. So this all in the current understanding, these internal shells are producing these GRBs, and they're hitting at different speeds, and so this is creating a time structure. In fact, this time structure in this light curve is telling us that they must be coming from very compact objects. But to our purposes, we have pretty much a smooth kind of evolution. Synchrotron evolution is pretty smooth.
So like the first time the burst happens, it's sort of a pulsed profile, and then afterwards we get a smooth afterglow.
Yes.
Is that correct?
That is correct, but that pulse doesn't have to be just one pulse. It could be a structure of pulses, or it could be a very highly variable structure. But yeah, pulse is kind of a right way to say, because the duration is so short. Yes.
Except it's not periodic. Okay, just to contrast.
Yeah, it's not periodic at all. Yeah, it's just one of a thing. Yeah.
Thank you.
Any other questions? Otherwise, we can close.
I just wanted to make a clarifying comment on the issue that was brought up about the coherent emission and the brightness temperature limit. Because I think the temperature of the physical temperature and this 10 to the 12 limit, K limit, was used interchangeably during the discussion. So the coherent emission is, concluded. Firstly, you can sort of say the brightness temperature is much more than the physical temperature, you can already begin to conclude about the non-thermal nature of it. And then when it exceeds 10 to the 12 Kelvin limit, that you can say that it's coherent emission. Is that correct? No?
Yeah, that's, yeah.
Ma'am, I have one last question.
Yes.
You mentioned sometime that a redshift of some 8.3 something corresponds to a very old age of the universe. So how exactly is that?
Yeah, so this is a you know about redshift, how, like, how a redshift is determined, and redshift is looking back time in the universe. So in fact, this one is an exercise which I want to ask you to figure it out, because how a redshift corresponds to a distance, and you can assume a standard a universe and standard Hubble constant and try to determine. So when I'm saying 630 million years, I'm assuming some value of Hubble constant and trying to determine. But redshift is a look back time in the universe, and then you can just determine based on the cosmological parameters about the universe. You can determine the distance of the universe, how much far away back in the time is. So redshift 0 is the current time right now, whatever is here now. So you can, in fact, it's a very interesting exercise for you to do it. So maybe I'll suggest you to do that.
Okay, ma'am. Thank you.
Sure. Yeah.
Actually,
You can answer me. You can email me the answer actually if you want.
actually,
Sorry,
there is a cosmology calculator as well in the web by Ned Wright. So
yes, but I
it.
wanted them to learn about
Yeah.
redshift. Yeah, but yeah, net cosmology calculator is what everyone uses it. But you should try to derive it using the formula.
Okay. Any other questions? Otherwise, we can
Can I
close.
just ask one question?
Yeah.
Ma'am, could you please go to the slide where you show the convective and radiative patterns in stars?
Yes, this one, right?
Yeah, this one. So if you look at 0.5 to 1.5 and then greater than 1.5, there's a sort of a flip in the pattern. So in 0.5 to 1.5, there's radiation dominant in the core and convection outside, and it's the other way around, being greater than 1.5. So is this sort of a very sharp transition, or is it more gradual?
No, it's not that sharp a transition. It's a gradual transition. I have just shown you this. And convection is kind of an instability which depends upon the temperature gradient. So how fast the nuclear reaction is happening. If radiation is incapable of taking all this energy out, so convective instability will develop. It depends upon the temperature gradient, but it is not this sharp at all. It is more gradual.
I'm curious to know, just by changing the mass, how such an, like, this is an inversion, right? Like entirely. So how
It is not about mass. It is how the photons are being transported from the core where they were produced to the surface, and ideally, for example, where convection is happening, some amount of radiation is also happening. It's just that convection is dominating the transport of energy, just because at the core the temperature gradient is so high that radiation is not able to take all the energy. So convection also participates. It's the movement of the matter itself participates in taking the energy. But you are right in the sense, if you take a slice of a star, so a fully convective star, it will have a very homogeneous distribution of the particles, right? Because of the convection, because the mass is participating. So that certainly is correct. So for example, if you take a very small convective region, the homogenization will be much more. It means, what does it tell you? That if you're talking about the core hydrogen, because of convection, there may be more mixing from the outermost zone. So maybe nuclear fusion will last slightly longer. So these kind of little effects do take into the stars. But in, say, for example, less than half solar mass star, where the whole star is convective, the whole of star will be participating in the nuclear fusion, because the whole star is quite homogeneous, more or less homogeneous, right? Those things do happen.
Thank you.
But is it all right to say that the key differences will emerge from the density and temperature gradients, radial dependence?
Temperature gradient is very critical here, I would say.
So that's what might decide which is, how
Right.
they emerge.
Exactly.
So can we conclude from this that there is a strong correlation between the temperature gradient and the mass? I mean,
Mass of the whole star?
yeah.
No, not. In some way, yes, because the temperature gradient will never be that high in a small mass star. But I would say this is not a sufficient condition to determine the mass of the star.
The more massive the star, the central temperature would be higher, right? In which case...
Central temperature is higher, the density, the temperature gradient is much higher, but I'm saying he's talking about the overall mass of the star. I'm saying we can certainly say that, but we can't conclude what is the mass of the star based on that.
No. I think what you're saying is more massive star might indicate different conditions, right? Much the way Sakya just pointed out, the central temperature could be higher and so on.
Yes, the gradient will be much higher. So convection will be will be there.
Right? Not the other way, not trying to estimate the mass from this.
Yeah, exactly. That is correct. Yes. Right.
But even in low mass stars where there is convection all around, your nuclear reactions to take place, the temperature will have to be above a certain critical value, right? So nuclear reactions will still be in the region where the temperature is high.
Temperature is high, but the gradient need not be high.
Gradient need not be high, but nuclear reactions will only take place where the temperature is high enough. Right?
Yes.
So it will not take place in the whole star, even if convection takes place.
Whole star, when I said, so that's why I said not in the restricted sense. It will take place in the larger region, not just at the very core, because the homogenization is little more. So that's what I meant. Yes.
Okay, thanks very much with great talk and all the exciting results from GMRT.